You take your first error, you square it. You take your second error, you square it. And logic of this is if you just add up errors and you're equally likely to, wander left and right, the sum of the errors you expect to average to 0. In any dimension, if it's isotropic way of making errors, you don't have a preference of making an error. So the first number you can get to characterize errors is the squares of errors because those are positive. And if you have, n measurements, n kicks, n dimensions, if you add these guys and you divide them by n, then you get the mean. And if you take a square root of this whole thing, it's called root mean square error. And it's just Pythagoras' theorem again, because, if I square the thing on the right, I will see that's what I mean by adding up squares to get the length of the vector. Now I will apply this in a deep and profound way, which is used in any setting where you have a noisy signal. So, a very typical setting today is biological settings where you have neurons firing and they have some probability of firing, so they are noisy, but their combined effect is not noisy. That's what we call brain. The other very important thing is when you're predicting the weather, you have both incomplete and noisy data, and you have noise in environment because the thing that you're measuring is being influenced by many things you're not measuring. Simplest assumption is that that's done in some kind of probabilistic way. So we do this all the time. And I'll give you a very short description of what noise does when you're trying to improve your weather prediction. For example, I have a paper that my collaborator has managed to prevent publishing over for 7 years in a row, even though she has given APS plenary conferences on this work. How does a baby bird learn how to sing? And how does it learn the tune? And that's done in noisy environment. And the way it does it is described by this well-known formula. So this is formula that relates covariances. Remember, covariances are these widths of Gaussian or root mean squares of distributions of area. And there are two kinds of covariance I'll describe, which is you're looking at a cloud of your data points at integer time n, and you fit it by ellipsoid like we have done in SVD part of this course, singular value decomposition, so that's how you fit the noise. But, somebody's kicking you with some noise of giving strength in different direction in a state space. So that's described by another covariance matrix. And you have a law of motion, which is non-trivial, and we'll only keep what happens in small neighborhoods for the law that's called linearist flow. So this equation was actually, there is a Russian called Lyapunov, who is credited with everything that ever happened in dynamics. He was a good, Russian nobleman who got a doctorate in 1892. He was interested in the stability of solar system. He was in contact with Henri Poincaré in Paris, being a cultured French-speaking kind of person. And he defended his doctorate where he gave this formula, which actually appears, as opposed to anything else that's called Lyapunov, appears in his thesis. And what he was, trying to prove is that if you're within some kind of error range, solar system will be stable. That's what his motivation was. Now, in 1930, this was reinvented by Uhlenbeck, who was an amazing Dutch physicist working at the University of Michigan. Thank you, Hitler. And his student Einstein. And that's the basis of everything you do on a stock market, all the stochastic processes. This, harmonic oscillator for these guys is called Einstein-Uhlenbeck. Simplest example of noisy program. Now, in the 50s and onward, if you try to improve your prediction of weather, you would keep measurements. You have supercomputer hummings and producing prediction from Navier-Stokes given data at a given moment. And then you make a next measurement and you see how wrong you were. And then you absorb that measurement. That's called data assimilation. You absorb that measurement into a prediction. And the way you do it is by so-called Kalman-Fichte prediction. And essential part of it is what I'll just explain to you, which is our, convolved Gaussians, really. So I'll illustrate just by one-dimensional noisy process. So suppose you have sequence time t, x prime is next time. There's some law that says if I was here, this is what happens next. But I get kicked around, so this is called stochastic term. And when you tell me I have a stochastic term, this process is called Langevin equation, Langevin flow. I have to tell you what kind of noise you have. So typically, I assume that the noise between two successive steps is uncorrelated. If I got kicked this way, the next kick doesn't care. This is called uncorrelated in time. But if I look at expectation values of products of them, that contains the square as well. That's this Kronecker delta. Average of squares cannot be zero. So that is characterized by a number which you measure experimentally. It's called diffusion constant. And the theory of this was one of the brilliant papers of Einstein in 2005. It's called theory of Brownian motion. But basically this says if I have kicks, I'm a particle that I'm kicked by smaller molecules, which I can't see, but I just wander around. Result is a diffusion constant of this strength per time step in time, basically. So that's how you think of noise, the simplest way. Now, how do you think of your law? You're given Newton, Navier-Stokes, something. So law is immutable and always true and cannot be messed with. So what the law does is, given some state in one-dimensional or million-dimensional state space, law predicts unique results. So if we are at position xn in state space, the law tells me time t later I'm away from it. And the linearized flow says, well, if I'm in a small neighborhood, I can measure the distance from where I am and predict where the distance is in the future. And the noise, and because this is linearization, we already learned this, it's the process of its propagation is called Jacobian Matrix. And that predicts where I am one step later. And the whole things, the words are, the neighborhood is advected by the flow, and the deterministic law takes something that looks simple like square initial time and stretches and squashes it according to the directions and eigenvalues of this matrix. And that's what determinism does. And we know how to do this in this course. We do it all the time. But when the noise comes in, I have to describe the initial point. I don't have it as a precise point. I have it as covariance, as an ellipsoid. And this is if I measure 1,000 points in this neighborhood, they sit in an ellipse. And if I compute the expectation value of component of in a z direction to component other direction and average it over all particles in a cloud, that's called covariance matrix. So, but this is just, our addition of errors glorified to higher dimensions, now we are looking at bilinear things. It's not just the error in one dimension, but more dimensions. So it gets replaced by this combination. So step later, what happens is every one of these neighboring points is advected deterministically by my linear law, M. Now I can take, these are just matrices of numbers. I can take them outside of this bracket of averaging. Then I'm averaging over this, that's called Q. And what it says that when I have an ellipsoid of initial condition, deterministic flow maps it into a different ellipsoid. And the law of the deformation is Jacobian on left, Jacobian transpose on the right. Now, I do this, and then I kick it. That's called noise. And I kick it by my rule, how I want to kick it. For example, I kick it either up and down, but not so much to the left and right. So that's some other matrix. And now the result is that if I had the ellipsoid of points at time t at n at time n plus 1, I'll get I get the center will move by deterministic law, but the neighborhood will deform, and it'll deform as a combination of where I was before, deformed by deterministic thing, plus my noise, and as covariance is add, this adds. And that's the law evolution of covariances. And that's what you do always when you're trying to combine your prediction. So, the supercomputers in Amsterdam are computing what Navier-Stokes says about weather 1 hour from now, if I knew it with this accuracy, which is given by this covariance. But there are imperfections. I know that, my measurements are not good. And what I expect is this covariance evolution. But all it is, it says covariances are the squares. And now, that's why people care about Fourier transform. This is essentially what Fourier did when he invented Fourier transforms. He was solving a heat equation, which is described by Gaussians, because if you have, a concentrated heat at the volume inside of a larger volume, could be air, could be fluid, then heat will diffuse in all directions, and that's described by Laplacians and by these covariances. So, so the very origin, very invention of Fourier methods come from this.